Hello guys, in this video I would like to discuss about some stoichiometry practice. So we'll do it together and we'll discuss the result. So for the first question, actually 22.4 gram sample of iron is going to be completely dissolved in dilute hydrochloric acid. And then the reaction is actually provided. So this is the iron, this is the hydrochloric acid, and it produces iron trichloride. This is the molecule and hydrogen gas. This is the unbalanced reaction, meaning that the atoms on the left side and on the right side is not yet equal. And in order for us to actually do stoichiometry calculation, we must ensure that the atoms both on the left side and on the right side are equal. So in this case, then we have to carefully consider this. So for example, now we see that the Fe on the left side and on the right side. We have Fe and then we have Cl and then we have hydrogen. On the left side initially we have one Fe, on the right side one Fe also. So yeah, we don't need to do anything here. For Cl we have one here and we have three here. And for hydrogen we have one and we have two here. Okay, so this is kinda tricky because we have to make sure that both left and right they have the same number of atoms. For those who are unfamiliar with balancing, actually what we need to do is that we need to multiply the number of atoms here. So for example, here we have 1 Cl and on the right side we have 3 Cl's, means that we have to multiply by 3. Yeah, but we have to put the number 3 in front of here, so means 3 HCl. But then it becomes quite confusing because here the number 1, it changes into 3 as well. Meaning that now we have a mismatch of hydrogen and on the left side and on the right side. So how come 2 becomes 3? Yeah, we can multiply it with maybe 1.5, let's say, yeah. Because if we multiply with 1.5, the 2 becomes 3. So let's say here 1.5. Is this allowed? Yes, this is allowed actually. But it might be uncommon for us to see like uneven number in chemical equation. So to make this all like a whole number, I could do like, for example, here everything I multiply by 2. So here I have 2 Fe and 6 HCl. It will form 2 FeCl3 and 3 hydrogen. Yeah. So 2, 6, 2, 3 here. If you leave it 1.5, that's still okay. Yeah. But it will make it a little bit confusing. Usually the sequence of balancing is that you have to make sure that the metal atoms are balanced first, then the non-metal atoms, and then hydrogen, and lastly oxygen. It should fit usually. Okay. So now question B asks for the number of moles of hydrochloric acid required to react completely with the iron sample. The thing is that fortunately we know already the mass. So the mass is actually 22.4 gram iron. Therefore we can actually find the mole here is equals to mass Fe divided by the atomic mass, or in this case AR of Fe. It's given 56. Yeah, it's already given here, meaning that we can use it. Yeah, ARFE, or you want to say MR because you are more familiar with MR. Yeah, that's also okay. Yeah, but technically it's AR because it's only one atom, only Fe, only. Do you need to multiply by 2? No, because this thing here is just actually showing us the recipe. The recipe of this reaction means 2 mole of Fe reacts with 6 mole of HCl, forms 2 mole of iron chloride and 3 mole of hydrogen. So if we still want to measure just the mole, this number 2 actually does not mean anything in the calculation here, M over MR, so don't worry. So we just need to plug in 22.4 gram divided by 56. I think this would be 0.4 mole if I'm not mistaken. Yeah, so this should be 0.4 mole. But this is only for Fe. Yeah, this is for this. But the question asks us for the mole of HCl actually. So how can we find that? Now imagine that here, 2 pieces of clothing, the price is $0.4. But now the question asks for us, what about 6 pieces of clothing? 6 is the number of HCl. So if I were you, I would find actually 1 piece of clothing is worth $0.3 because I divided 2 with 0.4, so that I get that 1 clothing is $0.3. Means that 6 here is 1.8 mole. So that the mole of hydrochloric acid required to react completely with the iron is exactly 1.8 mole. Finally, we are asked to calculate the mass of iron chloride produced in the reaction. Don't forget we have the triangle. Mole is equal to mass over molecular mass. Therefore, if we are asked to find the mass, we will have mole multiplied by DMR of FeCl3. So it will be 1. Oh no, it's not 1.8, yeah. It's 1.8 is actually for HCl. So we still have to find the mole of FeCl3. FeCl3, we see that it is actually 2. So imagine 2 pieces of clothing and the price is 0.4 mole. Then we also ask for the price of 2 pieces of clothing. Then I guess 2 pieces of clothing would still be 0.4 mole as well. So here it's 0.4 mole. Yeah, the information is obtained from question, actually from the question. Yeah, 22.4 gram Fe means we divide by the MR, we get the mole of Fe, and then we can find the mole of everyone in the reaction. So here actually 0.4 mole, and the MR of FeCl3 is like 56 plus, then we have 3 Cl atoms. Cl is 35.5. So 3 multiplied 35.5. Okay, so we have 0.4 mole multiplied 3, 105, 106.5 and 56. Yeah, let me grab my calculator. So for any molecular mass calculation, you have to take into account all the atoms. So it should be 162.5. Therefore, the final mass should be 65 gram. So this is the mass of iron chloride produced. We have to know that iron 3 chloride is actually something like this. Iron 3 plus 3, and then it contains 3 Cl. So if we want to measure only the mass of the iron, then we are going to calculate what is called the percentage, by mass. So now FeCl3. If we want to consider only the mass of the Fe, then we have to know what is the percentage of Fe atom inside this 65 grams, right? Because for example here, 65 grams, it is divided into Fe atoms and Cl atoms in FeCl3. But how do we know the percentage? Then we can actually do what is called by percentage of an atom. Let's say that here, percentage of an Fe is actually the atomic mass of Fe, like for all Fe. But here it is only 1, so we only use 1 Fe divided by the atomic mass of the Cl. Oh no, the atomic mass of the molecular mass of the everything of FeCl3. Okay, multiplied by 100%. So this will be the percentage of Fe. So now let's calculate. So 56 from the information given for us, because Fe, if I'm not mistaken, also if you see from the periodic table, it's 2656, and then for Cl it's 1735.5. so we also have the mass here. For FeCl3 we already calculated it's 162.5. if we multiply this with 100%, then we get 162.5, around 34.46%. Meaning that around 34.46% of the molecule consists of Fe atom. But now we can try and see the percentage of Cl atom. So it means that ArCl, yeah, divided by the Mr of FeCl3, so the everything, multiplied 100%. So now we have 3 Cl. So don't forget then that in FeCl3 we have 3 Cls, meaning that we multiplied the Ar by 3, we divide by everything, and then we multiply by 100%. So means we have 106.5 over 162.5 multiplied 100%. So we will get, actually it should be the remaining, which is 65.54%. So if you sum these two up, then they will be 100% exactly, meaning that our calculation is correct and the molecule consists of only Fe and Cl atoms. This is called percentage by mass. We calculate the percentage of an atom by dividing all the weight of that atom with the weight of the molecule multiplied by 100%. So feel free to take notes on this, because this can be tricky. Many students actually forget to multiply the number of atoms, which is quite important. In this case, the Cl, it has 3 Cl atoms. So now we know that the percentage of Fe is 34.46% of the whole 65 grams, meaning that the mass of Fe atom only is 34.46% multiplied by 65 gram. So we will have 65, around 22.4 gram. Oh well, kinda makes sense. Yeah. It seems that nature has a unique way of returning the atoms back to us, because here you see that on the left side we have 22.4 gram iron here, and then on the right side, supposedly the number of iron should be the same, which this calculation actually proves. But don't worry too much, technically you can find it this way. Now let's go to the second question. It's a Haber process. So it is used industrially to manufacture ammonia. There is an unbalanced equation. We have to write the balanced equation. So now let's see the left hand side and the right hand side. Let's balance this together. And we have nitrogen atom, and then we have hydrogen atom. Left hand side nitrogen we have 2, right hand side we have 1. Left hand side hydrogen we have 2, right hand side we have 3. So now right hand side nitrogen must be multiplied by 2, so that it will be 2, it will be balanced, meaning that we have to multiply this with 2. So we put a number in front, but the consequence is that the hydrogen would also accidentally become 6, because now we put 2 in front of NH3. Therefore, now for the hydrogen, the left hand side 2, right hand side 6. So we have to multiply this with 3. Then we put number 3 here. No, sorry. It should be in the hydrogen part. Yeah. So the equation will be N2 plus 3 hydrogen forming 2 ammonia. Something like this. Well, you can argue that it's actually a reversible reaction, but in this case, let's focus only on the reaction. So now for the second question, a chemical plant they want to produce 85 gram kilo of ammonia, which is this thing. Calculate the mass of nitrogen and the mass of hydrogen. We want the final answer to be in kilogram. So now, we have to find the mole first. We know that the mass of NH3 here, ammonia, is 85 kilo. But the mole is actually mass over MR in gram. So we have to change this in gram first. I prefer in grams. Or, you can use kilomole. That's okay. But that's not very common. But for the sake of simplicity, I convert this to gram. So now I can find the mole of NH3, which is the mass of NH3 divided by the MR of NH3. So it's like 85,000 gram divided by NH3. So ammonia is 714, hydrogen is 11. So NH3 will be 14 plus 1 multiplied 3, 17. Meaning that the mole of ammonia that is produced will be 5,000 mole. So now imagine that 2 pieces of clothing, the price is $5,000. Then what will be one price of clothing? It will be 2,500 mole. If 2 pieces of clothing is 5,000, so one piece is 2,500, meaning that 3 pieces would be 7,500 mole. So from this we can find the mass of each. So the mass of nitrogen would be mole multiplied MR of nitrogen. So nitrogen is 14, but we have 2 nitrogen atoms, so 28. So 2,500 multiplied 28, it will be 70,000 gram or 70 kilo. Because gram to kilo means you divide by 1,000. And then here, mass of hydrogen, meaning that mole of hydrogen multiplied by MR of hydrogen. Hydrogen mass is 1, but hydrogen is H2, so you need to multiply by 2. So here mass of hydrogen would be 7,500 multiplied by 2, so 15,000 gram or around 15 kilo. So that's the mass of nitrogen and hydrogen required to produce 85 kilogram of ammonia. The key takeaway simply say that if you have the mass, given the periodic table that you will know the molecular mass of a molecule, you would surely be able to find the moles, and then you would be able to find the information for most of the thing in the reaction. Finally, now you have to write your own reaction. Glucose C6H12O6 is an important source of energy for humans. It undergoes aerobic respiration, reacting with oxygen to form carbon dioxide and water. Write the balanced chemical equation. So glucose, it will react with oxygen to form carbon dioxide and water, CO2 and H2O. So now we have to balance this. You can do it slowly. Wait, let me write it here. So C6H12O6 plus O2, CO2 and H2O. So left and right, carbon, hydrogen, oxygen. Left 6, right 1, hydrogen is 12, right only 2, oxygen we have 8, so 6 plus 2, and then we have 3 here. Okay, so initially on the right side we must multiply by 6, so that carbon will be 6. Accidentally, the oxygen here now becomes 12 and 1, so 13. So far 13. Okay, for hydrogen on the left side it's 12, on the right side it's only 2, so we multiply by 6 again, become 12 and 12 now. This number 12 we put here. accidentally the oxygen now will become, this is 12, this is 12, so 24. Here it's not 12, but here it should be just 6. Yeah, let's say one oxygen. So it's not 24, but it's 18 actually. Therefore, here we just need 12 more. Assuming that we don't want to change this 6, we need to add just 6 more. 6 more. So let's just multiply this with 6. Because if we multiply this with 6, we will have 12, and then we have 6 oxygen, meaning that we have 18 in total, right? So it's kinda actually trial and error for the balancing part, guys. So yeah, you have to get the sense of this. Yeah, but this is 6, this is 6, and this is also 6. Now a portion of food contains 36 grams of glucose. We have to calculate the mass of carbon present in this amount of glucose. So now we have to calculate the percentage of carbon, which is the mass of carbon, multiplied by 6. Why? Because we have 6 carbon atom, divided by the molecular mass of C6H12O6. So carbon is actually 612, hydrogen is 11, and oxygen is 816. So now we have the mass of everything. So carbon multiplied by 6 is 12 multiplied 6, C6, so 12, 6, 1, 12, and then 16 times 6, meaning that we have 72 over 180, or multiplied by 100%, it will be around 40% exactly. So 40% of your glucose is carbon. So if you have 36 grams of glucose, so mass of carbon will be 36 grams multiplied 40%, or around 14.4 grams. Okay, finally, let's calculate the mass of water produced when 36 grams of glucose is completely metabolized. Okay, so now we have the reaction. Yeah, let me use this reaction here. Plus 6 oxygen, 6. Okay, so 36 grams of glucose. Well, we have to find the mole first. So the mole of glucose is the mass of glucose divided by mR of glucose, which is 36 grams divided by 180. We already calculated this in the previous number. Yeah, so this thing here is actually the mR of glucose. This thing here, the yellow part. So here it means that we have around 0.2 mole of glucose. So let's say that here, one piece of clothing, the price is $0.2. So what will be the price of 6 pieces of clothing? It will be $1.2, 6 times. So the mass of water will be the mole multiplied mR. So 1.2 mole multiplied mR of water, H2O. So 1 hydrogen atom, 2 hydrogen atoms and 1 oxygen atom, so 18. So in this case, it will be around 21.6 grams of water produced. Okay, so I hope that this small practice can be helpful. I will leave the notes also here for you. I'll give the link in the video when if you would need this maxim. Hope it's useful. Thank you, guys.